Hello and welcome everyone to Sciencera. In this video, we are going to discuss acids and bases, functional groups from Organic Chemistry 7th edition by L.G. Wade. We are going to start from polarity of bonds and molecules. Polarity of bonds and molecules. First, we're going to discuss bond dipole moments. Bond polarities can range from non-polar covalent through polar covalent to totally ionic. In the following example, ethane has a non-polar covalent carbon-carbon bond. Methylamine, methanol, and chloromethane have increasingly polar carbon-nitrogen, carbon-oxygen, and carbon-chlorine covalent bonds. Methyl ammonium chloride has an ionic bond between methyl ammonium ion and chloride ion. The polarity of an individual bond is measured as its bond dipole moment, which is defined as the amount of charge at either end of the dipole and the distance between the charges. Dipole moments are expressed in units of dib, d, where one dib is equal to 3.34 times 10 to power 3 coulombs per meter. Dipole moments are measured experimentally and they can be used to calculate other information such as bond length and charge separation. The positive end of the crossed arrow correspond to the less electronegative partial positive charge end of the dipole. Next, we are going to look at molecular dipole moments. A molecular dipole moment is the dipole moment of the molecule taken as a whole. It is a good indicator of a molecule's overall polarity. Molecular dipole moment can be measured directly in contrast to bond dipole moment, which must be estimated by comparing various compounds. The value of the molecular dipole moment is equal to the vector sum of the individual bond dipole moment. This vector sum reflects both the magnitude and the direction of each individual bond dipole moment. In carbon dioxide, the bond dipole moments are oriented in opposite direction, so they cancel each other out. Let's look at the example of formaldehyde. Formaldehyde has one strongly polar carbon-oxygen bond and carbon dioxide has two. We might expect carbon dioxide to have large dipole moment, but its dipole moment is actually zero. The symmetry of the carbon dioxide molecule explains this surprising result. The structure of formaldehyde and carbon dioxide shown in the diagram together with their electrostatic potential map. These electrostatic potential map shows the direction of the bond dipole moment with red at the negative end and blue at the positive end of the dipole. In carbon dioxide, the bond dipole moments are oriented in opposite direction, so they cancel each other out. The figure at the right hand corner of the page shows some example of molecular dipole moment. Notice the dipole moment of carbon-hydrogen bonds is small, so we often treat carbon-hydrogen bond as nearly non-polar. Also note that the tetrahedral symmetry of CCl4 position the 4 carbon chlorine dipole moment in the direction, so they cancel each other out. Lone pair of electron contributes to the dipole moment of bond and molecules. Each lone pair corresponds to the charge separation, with nucleus having a partial positive charge balanced by the negative charge of the lone pair. The figure shows the effect of lone pair on dipole moment. Lone pair can make large contribution to the molecular dipole moment. Intermolecular forces. Strength of attractions between molecules influences the physical property of molecule. For example, its melting point, boiling point, and solubility of compounds. The intermolecular forces are classified into three categories. London depression forces, which is the weakest forces, dipole-dipole forces, medium strength forces, then hydrogen bonding in molecules with fluorine and hydrogen bond, OH bond and NH groups. These are the strongest bonding, or they have the strongest intermolecular forces. London depression have weakest and hydrogen bonding has the strongest intermolecular forces. Let's look at the each one separately. Dipole-dipole forces. Attractive intermolecular forces resulting from attraction of positive and negative end of the dipole moment of the polar molecules. Polar molecules are mostly orientated in the lower energy positive to negative arrangement, and the net force is attractive. This attraction must be overcome when liquid vaporize, resulting in areas resulting in larger heat of vaporization and higher boiling points of strongly polar compound. So the dipole-dipole interaction results from the approach of two polar molecules. If their positive and negative ends approach, the interaction is an attractive one. If the two negative ends or two positive end approaches, the interaction is repulsive. In a liquid or solid, the molecules are mostly oriented with positive and negative end together, and the net force is attractive. Next is London depression force. This is the principal attractive force in nonpolar molecules. It arises from temporary dipole moment induced by the other molecules. Isomers with large surface area have higher boiling points and greater potential of the London force attraction. This is the one of the van der Waals forces. A temporary dipole moment in molecule can induce a temporary dipole moment in a nearby molecule. An attractive dipole-dipole interaction results for a fraction of a second. Main force in non-polar molecule is London depression forces. Large atoms are more polarized. Hydrogen bonding. Strong dipole-dipole attraction. Organic molecules must have FH, OH or NH to be able to form a hydrogen bond directly attached to the hydrogen group. The hydrogen from one molecule is strongly attracted to a lone pair of electrons or oxygen of another molecule. So the hydrogen bonding have strong dipole-dipole attraction between OH and NH bonds, can participate in hydrogen bonding. Alcohol forms stronger hydrogen bond than amines. OH is strongly polarized than nitrogen hydrogen bond. Why alcohol form strong hydrogen bonds than amines? Because oxygen is more electronegative than nitrogen, thus the OH bond is more strongly polarized than NH bond. Polarity effects on solubilities. The general rule is that like dissolve like. So the polar substance dissolve in polar solvent and non-polar substances dissolve in non-polar solvent. We consider four different cases: a polar solute with polar solvent, a polar solute with non-polar solvent, a non-polar solute with non-polar solvent, and non-polar solute with a polar solvent. We use sodium chloride and water as an example of polar solute and solvent, and paraffin wax and gasoline as example of non-polar solute and solvent. So let's look at the first one. Polar solute in polar solvent dissolves. When you think about sodium chloride dissolving in water, it seems remarkable that the oppositely charged ion can be separated from each other. A great deal of energy is required to separate these ions. A polar solvent such as water can separate the ion because it solvates them. If water is solvent, the solvation process is called hydration. As the salt dissolves, water molecules surround each ion with appropriate end of the water dipole moment next to the ion. The oxygen atom of the water molecules approach positively charged sodium ion. Water hydrogen atoms approaches the negatively charged chloride ion. Because water molecules are strongly polar, a large amount of energy is released when sodium and chloride ions are hydrated. This energy is nearly sufficient to overcome the lattice energy of the crystal. The salt dissolves partly because of the strong solvation of water molecules and partly because the increase in entropy, randomness or freedomness of the movement when it dissolves. As shown in the first figure, polar solute in water, the hydration of sodium and chloride ion by water molecules overcome the lattice energy of sodium chloride and the salt dissolve. Next case is polar solute in a non-polar solvent. It doesn't dissolve because like dissolves like. This is the general rule. If you stir sodium chloride with nonpolar solvents such as turpentine or gasoline, you will find that salt does not dissolve. The nonpolar molecules of these solvents do not solvate ions very strongly, and they cannot overcome the large lattice energy of the salt crystal. This is the case where attraction of ions in a solid for each other are much greater than the attraction of the solvent, as shown in the figure 2. Polar solute in a nonpolar solvent. The intermolecular attraction of polar substances are stronger than their attraction of nonpolar solvent molecule. Thus, a polar substance does not dissolve in nonpolar solvent. Number 3 is nonpolar solute in a nonpolar solvent. They dissolve. Paraffin wax dissolve in gasoline. Both paraffin and gasolines are mixture of nonpolar hydrocarbon. The molecules of nonpolar substance paraffin are weakly attracted to each other, and these van der Waals attractions are easily overcome by van der Waals attractions with solvent. Although there is a little change in energy when nonpolar substances dissolve in nonpolar solvent, there is a large energy increase in the entropy. As shown in the figure on the right, nonpolar solute in nonpolar solvent, the weak intermolecular attraction of nonpolar substance are overcome by the weak attraction of a nonpolar solvent, and the nonpolar substances dissolves. Next case is nonpolar solute in a polar solvent. They do not dissolve. Nonpolar substances that do not dissolve in water are called hydrophobic or water hating, and polar substances that readily dissolve in water are called hydrophilic, water loving. As shown in the figure, nonpolar solute in a nonpolar solvent, water, nonpolar substances are hydrophobic. They do not dissolve in water because of unfavorable entropy effect associated with forming a hydrogen bonded shell of water molecules around a nonpolar molecule. Next concept we're going to discuss is Arrhenius acids and bases. Acidic compounds were first classified on basis of their sour taste. The Latin word acidus sour and acetum vinegar gave rise to our modern term acid and acetic acid. Alkyne compounds bases were substances that neutralizes acids such as limestone and plant ashes, alkali in Arabic. Savant Arrhenius introduced the Arrhenius theory, which defined acid as substance that dissociate in water to give hydronium ion. The stronger acids such as sulfuric acid were assumed to dissociate to a greater degree than weaker acids such as acetic acid. According to the Arrhenius definition, bases are substances that dissociate in water to give hydroxide ions. Strong bases such as sodium hydroxide were assumed to dissociate more completely than weaker sparingly soluble bases such as magnesium hydroxide. Remember that the acidity and basicity of the aqueous solution is measured by the concentration of hydronium ion. The value also implies the concentration of hydroxide because these two concentrations are related by water ion product constant, which is 1 times 10 to power minus 4. In a neutral solution, the concentration of hydronium and hydroxide ions are equal, which means that the hydronium ion is equal to hydroxide ion with and the value is 1 times 10 to power minus 7 in a neutral solution. Acidic and basic solutions are defined by an excess of hydronium or hydroxide ion. In acidic solution, hydronium ion is greater than 10 to power minus 7 moles and the hydroxide ion is less than 10 to power minus 7. In basic solution, it is opposite. Because these concentration can span a wide range of values, the acidity and basicity of a solution is usually measured on a logarithm scale. The pH is defined as negative logarithm of H3O plus ion concentration, which means pH is minus log 10 times the concentration of hydronium ion. A neutral solution has pH of 7, an acidic solution has pH less than 7, and a basic solution has pH greater than 7. Bronsted Lowry acid and bases. A Bronsted Lowry acid is any species that can donate a proton, and Bronsted Lowry base is any species that can accept a proton. These definitions also include all Arrhenius acids and bases because compounds that dissociate to give hydronium are proton donor and compounds that dissociate to give hydroxide are proton acceptor. Hydroxide ion accepts a proton from water to form water. In addition to Arrhenius acid and bases, the Bronsted-Lowry definition include bases that have no hydroxide ion yet can accept protons. Consider the following example of acid donating proton to base. NOH is a base under either Arrhenius or Bronsted-Lowry definition. The other three are Bronsted-Lowry bases but not Arrhenius bases because they have no hydroxide ion. When a base accepts a proton, it becomes an acid capable of returning that proton. When an acid donates its proton, it becomes base capable of accepting that proton back. One of the most important principles of Bronsted-Lowry definition is concept of conjugate acid and bases. For example, NH4 plus and NH3 are conjugate acid-base pair. NH3 is a base when it accepts a proton. It is transformed into its conjugate acid, NH4 plus. Many compounds, water for instance, can react as either an acid or base. Strength of acid and bases. Strength of an acid should reflect its tendency to protonate a base by donating a proton. Similarly, the strength of a base should reflect its tendency to deprotonate an acid by accepting a proton. Let's look at the strength of acid first. The strength of a Bronsted-Lowry acid is expressed as it is in a Arrhenius definition by extent of its ionization in water. The general reaction for an acid HA with water is as follows. Acid reacts with water to give hydronium ion plus base. Ka is called the acid dissociation constant and its value indicates the relative strength of an acid. The stronger the acid, the more it dissociates, giving a larger Ka value. The acid dissociation constant vary over a wide range. Strong acids are almost completely ionized in water and their dissociation constant are greater than 1. Most organic acids are weak acid with Ka value less than 10 to power minus 4. Many organic compounds are extremely weak acid. For example, methane and ethane are essentially with Ka value less than 10 to power minus 40. Because they span such a wide range, acid dissociation constant are often expressed as logarithm scale. pKa of an acid is defined just like a pH of a solution as negative logarithm of Ka. Strong acids generally have pKa value around 0 or even negative, and weak acids such as most organic acids have pKa value of greater than 4. Weaker acids have larger pKa value. As the pKa value increases, the Ka value decreases. Strength of a base. Strength of an acid is inversely related to the strength of its conjugate base. For example, an acid to be a strong, its conjugate base must be stable in its ionic form. Otherwise, acid would not easily lose its proton. Therefore, conjugate base of a strong acid must be a weak base. On other hand, when an acid is weak, its conjugate base must be strong base. In the reaction of an acid with base, the equilibrium generally favors the weaker acid and base. The strength of a base is measured much like the strength of an acid by using the equilibrium constant of hydrolysis reaction. The equilibrium constant Kb for this reaction is called base dissociation constant for the base A-. Because this constant spans a wide range of value, it is often given in algorithmic form. The negative algorithm base 10 of Kb is defined as pKb. When we multiply Ka by Kb, we can see how the acidity of an acid is related to the basicity of the conjugate base. In an aqueous solution, the product of Ka and Kb must always equal the ion product constant of water, which is Kw equals 10 to power minus 14. If the value of Ka is large, the value of Kb must be small. That is, stronger an acid, the weaker the conjugate base. Similarly, a small value of Ka weak acid implies a large value of Kb strong base. Equilibrium position of acid and base reaction. How do we know which way the reaction goes and which species are favored by equilibrium? We decide this by using three principles. The acid-base equilibrium favor formation of weaker acid and weaker base. The weaker acid has larger pKa and the weaker base has larger pKb. And third one is the weaker acid and weaker bases are always on the same side of the equation. Both are reactants or either both are products. Problem solving strategy predicting acid base equilibrium position. Let's summarize the step involved and then use the step to work through a particular difficult problem. The step we used was step 1. Complete the reaction if necessary and label the acid and bases on each side. Step 2. Assign pKa or pKb values from table or by analogy with similar compounds. Note that extensive list of pKa value is given. Step 3. Calculate any needed pKa or pKb value using the fact that pKa plus pKb will give you 14 for a conjugate acid-base pair. Choose the side with weaker acid or weaker base, larger value of pKa or pKb as favored. The difference in pKa or pKb value shows how strongly the side is favored. Next let's work through an example. As an example, the following reaction is strongly basic, one that cannot take place in water, because water would protonate the base involved. In fact, this reaction is usually done in liquid ammonium solution. Propyne reacts with sodium amide to give sodium propanide plus ammonia. In step 1, in this reaction, a very weakly acidic proton is transferred from propyne to amide ion to give propanide, anion and ammonia. Propyne serve as weak acid and ammonia is conjugate acid of the amide ion, a powerful base. The pKa value is shown in table and appendix as about 36. When a pKa is this large, it depends on the solvent and it is difficult to measure. The pKa of propyne is not listed in table, but we can estimate it. The table shows pKa of acetylene as 25. This should be a good approximation of the pKa of propyne. The pKb of amide anion can be formed by subtracting the pKa of ammonia from 14. 14 minus 36 will give you minus 22. This large negative pKb indicate an unusually powerful base. The pKb of propionide ion is 14 minus 25 equals minus 11. This is also a very strong base but not as strong as amide ion. Step 4. We can compare pKa value or pKb value. Either way, the products are weaker acid and weaker base, but by about 11 pKa unit. The products are strongly favored in this reaction and reaction should complete. Solvent effects on acidity and basicity. Water is amphoteric in nature. It can react as both an acid or base. Its conjugate acid is H3O plus or hydronium ion and its conjugate base is hydroxide ion. When water is solvent for a reaction, it is present in large excess. Any acid that is stronger than hydronium ion with pKa value equal minus 1.7 does not survive in water but react with water to give hydronium ion. For example, if we add HCl gas pKa equals minus 7 to water, it immediately reacts exothermically to give hydronium ion, a weaker acid. Water narrows the possible ranges of acid strength and base strength to the value of pKa greater than -1.7 and value of pKb greater than -1.7. Any acid with pKa more than negative than -1.7 will be leveled to hydronium ion with pKa equals -1.7. Any base with pKb more negative than -1.7 will be leveled to hydroxide with pKb equals -1.7. Alcohols react with both strong acid and strong base just like water does. For example, strong acid protonate ethanol to give protonated ethanol and acid with pKa equals -2.4. Any acid with a pKa that is more negative than -2.4 will donate a proton to ethanol. Strong bases deprotonate ethanol to give ethoxide ion, a base with pKb equals -1.9. Any base with pKb that is more negative than -1.9 will become protonated in ethanol solution. Effect of size and electronegativity on acidity. How can we look at a structure and predict whether a compound will be strong acid or weak acid or not at acid at all? To be a Bronsted Lowry acid, a compound must contain a hydrogen atom that can be lost as a proton. A strong acid must have a stable conjugate base after losing the proton. Stability of conjugate base is good guide to acidity. More stable anion tend to be weaker bases and their conjugate acid tends to be a stronger acid. Some of the factors that affect the stability of conjugate bases are electronegativity, size and resonance. Electronegativity. A more electronegative element bears a negative charge more easily, giving a more stable conjugate base and a stronger acid. Electronegativity is increased from left to right in a periodic table. Size. The negative charge of an anion is more stable if it's spread over a large region of space within a column of periodic table. Acidity increased down the column as the size of an element increased. To evaluate or compare the acidity of acid, consider the stability of their conjugate bases. To compare the basicity of the bases, consider stability of conjugate acid. In comparison of similar bases, a negative charge is generally more stable on a larger atom or more electronegative atom. Enhanced stability of base increase the strength of its conjugate acid. Acidity trend. Figure summarizes these two effects of size and electronegativity using part of periodic table to show pKa of acid formed when each element is combined with enough hydrogen atom to fill its valence. Acidity increases towards the right, increasing electronegativity, and downward to increasing size on a periodic table. A smaller or more negative value of pKa implies a strong acid and more stable conjugate base. Inductive effect on acidity. The magnitude of inductive effects depend on the number of bonds between the electronegative element or another electron withdrawing group and the site of negative charge. Note how adding a chlorine atom to butanoic acid increases its acidity. An effect is larger if chlorine atom is closer to the acidic group. Stronger electron withdrawing group stabilizes the anion of conjugate base more than a weaker groups do, leading to the stronger acid. Fluorine is more electronegative and stronger withdrawing group than chloride, making fluoroacetic acid a stronger acid than chloroacetic acid. This trend continues through the other halogen substitute acetic acid. Multiple electron withdrawing group stabilizes the conjugate base and increase the acidity more than the single group does. When a problem asks you to compare acidities or explain an acidity, you should consider the structure and stability of conjugate base, and factors that stabilizes the conjugate base will increase the strength of an acid. Acidity is increased by three things: stronger electron withdrawing substituent, additional electron withdrawing substituent, and closer proximity of electron withdrawing substituent to the acidic group. Hybridization effect on acidity. Stability depends on hybridization state of orbital where it resides. The acidity of NH bond varies with hybridization in order sp3 is less than sp2 and which is less than sp. Electron in sp3 hybrid orbitals are on average farthest from the nucleus. Electrons in sp2 hybrid orbitals are held closer and more tightly. Electrons in sp hybrid orbitals are held closest and tightest of all. When an acid donates a proton, the conjugate base is left with two electrons that once bonded it to the proton, and often a negative charge. This lone pair of electron and negative charge may be delocalized over two or more atoms by resonance. The amount of stabilization that occurs through resonance depends on how electronegative the atoms are and how many share the charge and the lone pair. In many cases, resonance delocalization is the dominant effect, helping to stabilize the conjugate base. For example, acetic acid is over 11 pKa units more acidic than ethanol as shown in the figure. This large difference is due to enhanced stability of acetate ion, which is conjugate base of acetic acid. The negative charge in acetate ion is delocalized over two oxygen atoms in contrast to ethoxide ion, which has negative charge localized on its single oxygen atom. Proton on carbon and nitrogen are also more acidic if they are located where the conjugate base is stabilized by resonance. Two of the stronger stabilizing groups are called cyano group and nitro groups. An amide is stabilized by resonance between amino group and carbonyl group. This resonance delocalizes the lone pair on nitrogen and make it less available for bonding to a proton. Resonance delocalization is most common type of stabilization. Resonance delocalization of charges on a base helps to stabilize the base, making it a weaker base and strengthening its conjugate acid. The strongest common stabilizing group are the carbonyl, cyano, and nitro groups. Lewis acids and bases. Lewis bases are species with available electron that can be donated to form new bond. Lewis acids are species that can accept these electron pair to form new bonds because a Lewis acid accepts a pair of electrons. It is called electrophile, from the Greek word meaning lovers of electron. A Lewis base is called nucleophile or lover of nuclei because it donates an electron to a nucleus with an empty or easily vacated orbital. We sometimes use color types for emphasis: blue for nucleophiles and green for electrophiles, and occasionally red for acidic protons. A nucleophile donates electrons and electrophile accept electrons. Acidic protons may serve as electron acceptor. Curved arrow red are used to show the movement of electron from nucleophile to an electrophile. The curved arrow formalism. The curved arrow formalism is used to show the flow of an electron pair from the electron donor to electron acceptor. The movement of each pair of electrons involved in making or breaking bond is indicated by its own separate arrow as shown in the reaction. In preceding reaction CH3O with CH3Cl, one curved arrow shows the lone pair on oxygen forming a bond to carbon. Another curved arrow shows the carbon-chlorine bonding pair detaches from carbon and become a lone pair of chlorine product. Curved arrow formalism is universally used for keeping track of the flow of electron in reaction. In this way, we show exactly what changes take place in a reaction as well as the detail of how those changes occur. The curved red arrow shows movement of electrons. Each arrow must begin at a pair of electron, either an unshared electron pair or a pair of electron in a bond. Each arrow should point towards where the pair of electron will be in the product, either forming a bond to another atom or residing as an unshared pair of an atom. Classes of compounds. Classification are based on functional group. Functional groups are the part of molecules where reaction usually occurs. Functional groups are distinct chemical units such as double bonds, hydroxy groups, or halogen atoms that are reactive. Most organic compounds are characterized by and classified by their functional group. Three broad classes of functional groups are hydrocarbons, compounds composed of only carbon and hydrogen. Second is compounds containing oxygen, and then compounds containing nitrogen. Hydrocarbons are composed of entirely carbon and hydrogen. Alkanes have single bond between the carbon. All carbons are sp3. Cycloalkane are sp3 carbon which forms a ring. Alkenes have double bond. Double bonds are present in the molecules of alkene and they are sp2 carbon. Cycloalkenes, they have double bond in a ring. Alkynes have triple bond present in a ring and they have sp carbons. Aromatic carbon contain a benzene ring. Alkanes. Naming alkanes. Alkanes are hydrocarbons that contain only single bond. Alkane names generally have an "ane" suffix and the first part of the name indicate the number of carbon atom. As shown in the table, how prefix in the name correspond with number of carbon atom. Naming of the compound nomenclature is covered in another video. So methane 1 and ane is the suffix used for alkane. So methane is 1 carbon compound. Ethane is 2 carbon. Eth for 2, prop for 3, bute for 4, pent for 5 and so on. Cycloalkanes are special class of alkanes in form of ring. The figure shows the Lewis structures and the line angle formula of cyclopentane and cyclohexane, the cycloalkanes containing 5 and 6 carbon ring respectively. Alkanes are the major component of heating gas, natural gas and liquefied petroleum gas, gasoline, jet fuel, diesel fuel, motor oil, fuel oil and paraffin gases. An alkyl group is an alkane portion of a molecule with one hydrogen atom removed to allow bonding to the rest of the molecules. Alkyl groups are named like alkanes. They are derived from with a "-ile" as suffix. Alkenes. Alkenes are hydrocarbons that contain carbon-carbon double bond. A carbon-carbon double bond is most reactive part of an alkene. So we say that double bond is the functional group of alkene. Alkene name end in the suffix "-ene". If the double bond might be in more than one position, then chain is numbered and the lower number of the two double bond carbon is added to the name to indicate the position of the double bond. Carbon-carbon double bonds cannot rotate and many alkenes shows geometric cis and trans isomerism. Cycloalkenes are also common. Unless the rings are very large, cycloalkenes are always the cis isomer and the term cis is omitted from the name. In a large ring, a trans bond may occur giving a trans cycloalkane. Alkynes. Alkynes are hydrocarbons with carbon-carbon triple bond as their functional group. Alkynes name generally have "-ine" suffix, Y-N-E suffix, although some of their common names, acetylene for example, do not conform to this rule. The triple bond is linear, so there are no possibility of geometric isomerism in alkynes. In an alkyne, four atoms must be in a straight line. These four collinear atoms are not easily bent into ring, so cycloalkynes are rare. Cycloalkynes is stable only if the ring is large, containing 8 or more carbon atoms. Aromatic hydrocarbons. The following compound may look like cycloalkanes, but their properties are different from those of simple alkenes. Aromatic hydrocarbons, also called arenes, are all derivatives of benzene, represented by six-member ring with three double bonds. This bonding arrangement is particularly stable. Just as generic alkyl group substituent is represented by R, a generic aryl group is represented by Ar. When a benzene ring serves as substituent, it is called a phenyl group abbreviated by PH. Compounds containing oxygen. Many organic compounds contain oxygen atoms bonded to alkyl group. The major classes of oxygen containing compounds are alcohol ethers, ketones, aldehydes, carboxylic acid, and acid derivatives. Alcohol contain the hydroxyl group as main functional group. Ethers contain two alkyl group bonded to an oxygen. Aldehyde or ketone contain carbonyl group and carboxylic acid contain carboxylic group. Let's look at each one in detail. Alcohols. Alcohols are organic compounds that contain hydroxy group as their functional group. General formula for an alcohol is ROH. Alcohol are among most polar organic compounds because hydroxy group is strongly polar and can participate in hydrogen bonding. Thus, the hydroxy group is hydrophilic and it confers solubility in water if hydrophobic alkyl part of the molecule is not too large. Some of the simple alcohols such as ethanol and methanol are miscible with water, but alcohols with more than 4 carbons have limited solubility in water. Name of the alcohols end in OL suffix from the word alcohol as shown in the following common alcohols: methanol, ethanol, propane 1-ol and propane 2-ol. Ethers. Ethers are composed of two alkyl groups bonded to an oxygen atom. General formula is ROR. The symbol R represents only another alkyl group either with the same or different from the first. Like alcohol, ethers are much more polar than hydrocarbons, but ether have no OH hydrogen, so they cannot form hydrogen bond. Ethers do form hydrogen bond with hydrogen bond donors such as alcohol, amines and water, enhancing their solubility with these compounds. Ethers named are often formed from names of alkyl groups and the word ether. Diethyl ether is the most common ether used for starting engines in cold weather. Aldehyde and ketone. The carbonyl group is the functional group of both aldehyde and ketone. A ketone has two alkyl group bonded to the carbonyl group. An aldehyde has one alkyl group and a hydrogen atom bonded to the carbonyl group. Ketone names generally have "-one" suffix, and the aldehyde name use either "al" suffix or the aldehyde suffix. Carbonyl group is strongly polar and it can form hydrogen bonds with hydrogen bond donors such as water, alcohol, and amines. Hydrophilic carbonyl group also allows aldehyde and ketones containing up to 4 carbon atoms to be miscible with water. Those with more than 4 carbons have limited solubility in water. Carboxylic acid. Carboxylic acid contains carboxylic group as their functional group. The general formula of carboxylic acid is RCOOH or RCO2H. Carboxylic group is combination of carbonyl group and hydroxy group, but this combination has different properties from those of ketones and alcohols. Carboxylic acid owe their acidity to resonance stabilized carboxylate anion formed by deprotonation. Systematic names for carboxylic acid use oic acid suffix, but historical names are commonly used. Formic acid was first isolated from ants, genus Formica. Acetic acid is found in vinegar, gets its name from Latin words sour or acetum. Propionic acid gives tangy flavor to sharp cheese, and butyric acid provides pungent aroma to rancid butter. Carboxylic acid are strongly polar, like ketone, aldehyde, and alcohol. The strong hydrophilic carboxylic group enhance their stability in water. Carboxylic acid derivatives. Carboxylic acid are easily converted to a variety of acid derivatives. Each derivative contains the carbonyl group bonded to an oxygen atom or another electron withdrawing element. Among these functional groups are acid chlorides, ester and amides. All of these groups are converted back to carboxylic acid by acidic or basic hydrolysis. Compounds containing nitrogen. Nitrogen is another element often found in functional groups of organic compounds. The most common nitrogenous organic compounds are amines, amide, and nitriles. Amines are alkylated derivatives of ammonia. Amides are carboxylic acid derivative with a nitrogen attached to carbonyl group. And nitriles contain cyano group. Amines are alkylated derivatives of ammonia. Like ammonia, amines are basic. Because of their basicity, naturally occurring amines often called alkaloids. Simple amines are named by naming alkyl group bonding to nitrogen and adding the word amine. Structure of a simple amines are shown below. Together with the structure of nicotine, a toxic alkaloid found in tobacco leaves. Nitrogen atom of an amine is hydrophilic because it can accept hydrogen bonds from water. If amine has NH bond, these can donate hydrogen bond to water. Therefore, many of amines containing up to 5 carbons atom are miscible in water. Next one is amide. Amide are acid derivatives that result from the combination of acid with ammonia or an amine. Proteins have structure of long chain complex amides. Amides are among the most stable acid derivatives. Nitrogen atom of an amide is not as basic as nitrogen atom of amine because electron withdrawing effect of carbonyl group. Amides form particularly strong hydrogen bond, giving them high melting point and high boiling point. Strongly polarized amide NH group NH hydrogen forms unusually strong hydrogen bond with carbonyl oxygen that carries a partial negative charge in polarized resonance form. The last functional group with nitrogen is nitriles. A nitrile is a compound containing cyano group. The cyano group has sp hybridized bonding. The cyano group is strongly polar by virtue of carbon-nitrogen triple bond, and most small nitriles are somewhat soluble in water. Acetonitrile is miscible with water. With this, we're going to end our topic of acid and bases functional group. Thank you for watching. If you like my video, don't forget to subscribe for more.